Hello and welcome to my video about gravitational fields. So the first thing you need to think about and keep in mind with gravitational field is that it really depends on your radius. Your radius is the most important thing when you're talking about a gravitational field strength, the acceleration due to gravity, right? Because the radius is squared. So this means we have this is called an inverse square proportionality or inverse square law. Okay, it's proportional, but only with inverse squares. So if you see here, the distance, the further you go, the significantly less field strength that there is. Okay, that's a concept that you need to know. But really, the formulas are all just this, right? So keep in mind, this guy here was from the last video, so the Fg equals G m1 m2 over r squared. But if we know Fg is mg, where it's one of the two masses, it doesn't really matter which, but they chose m1, right? Then we can actually go ahead and cancel m1 in both places, and so we're left with G, capital G, m2 over r squared equals g, lowercase g, right? And that's where this formula comes from. So nothing too crazy, nothing actually new technically, sort of, but this is the formula that we're going to use basically for the rest of this. So here are a couple example questions. Let's see if we can get all of them showing at the same time with my formula. I can only get 3 at a time, so we'll show 3 and then we'll do then you can pause the video, try them out, and press play again when you're ready. Okay, so this first one's going to be pretty easy. What's the acceleration of gravity on the moon if it has a radius of that? Well, if the gravity is well, we're looking for the gravity, so we've got g, which is 6.67 times 10 to the negative 11, and then the mass, which is 7.348 times 10 to the 22 kilograms. Oh, well, we don't need to have the units, actually. Didn't do the units for the other one. Actually, that has a 4 there. And then this one is the radius, which is let's do this, 1.7374 times 10 to the 1, 2, 3, plus it's kilometers, so another 3, so 6, because it has to be in meters. This is the big concept, in meters, okay? And then that's squared, so what do we get? Well, let's plug it all in. So 6.674 times 10 to the negative 11 times by 7.348 times 10 to the exponent 22, and then 1.7374 times 10 to the 6. Oh, I screwed up. I forgot to square it at the bottom. Yeah, see? I make mistakes too. Okay, there you go. So 1.6. There you go. 1.62. So 1.62. This is meters per second squared. And actually, we should probably have one more. 1.625. Okay, so we have this as our acceleration due to gravity on the moon's surface. Okay, so here's another question. The ISS orbits at a height of that above the Earth's surface. If the Earth has a radius of that and a mass of that, what does an astronaut actually experience? Okay, so this is going to be a very similar question to what we had before, but your radius is going to be the Earth's radius. Let's do it this. Earth's radius plus the orbital height. Okay, I don't want to write it all out because it takes a bunch of time, but hopefully you can see that. When I type it in my calculator, you'll be able to see it as well. So let's type it in now. So this is going to be 5.972. No, that's the wrong spot. 6.371. And then plus 408 times 1,000. That's the easiest way of doing that. And then we're going to change this to be times 10 to the 24 and 5.972. Probably would have been easier if I just retyped the whole thing, hey? But anyways, I went back and adjusted everything. I believe this is correct now. 3 plus 3, yeah. So there you go. So the gravity that an astronaut experiences on the ISS is 8.67. Yeah, we're just going to leave it there. Now, you're all thinking to yourself, wait a second, but I thought they were weightless. And absolutely they were weightless on the ISS, but they are getting a gravity. They're getting this acceleration. They're always accelerating. Where are they accelerating to? Well, they're accelerating to the Earth. But they're accelerating in a orbiting manner. So they're always accelerating inwards towards the Earth, which is always pulling them back into the orbit. And that is actually what's happening. We'll talk more about that in the next video, but it's a really cool piece of information. They are getting gravity. It's just that they're falling towards the Earth at 8.67 meters per second squared at all times. It's beautiful. Okay, let's keep going. The gravity of the surface of Mars is... Oh, and I wish I would have done this earlier. Sorry about that. I'm just going to put it into... Nope, not like that. It's just easier if I do this. It looks prettier. There you go. Okay, so the gravity of the surface of Mars is 3.71 meters per second squared. If the planet has a radius of that, then what is its mass? So now we're going to solve for the mass of the planet. So mass of Mars over the radius squared. So we're going to solve for the mass. So it's going to turn into gr squared over capital G equals mass of Mars. Okay, so now we can plug in all those values, and we're going to restart from the beginning because I don't want to do the same thing like last time. Times the radius, which is 3.3895 times 10 to the exponent 6 squared over gravitational constant 6.674 times 10 to the exponent negative 11, and that means the mass of Mars is 6.386 times 10 to the 23. 6.386 times 10 to the 23 kilograms. Now with sig digs, 6.39 times 10 to the 23 kilograms. All right, let's do one more question here. I highly recommend you pause the video, try it out yourself, and see what you get. So we're looking for, we have this formula here, so first of all, but we're looking for the radius this time, the radius of Venus. at the surface. Okay. Now you'll notice here actually that honestly the surface of Venus that has a very close gravity to Earth compared to Mars. Mars is like less than half of Earth, and this is almost all the way to Earth. So 9.81, right? It's pretty close to Earth's gravity. Anyways, let's multiply by r squared on both sides and divide by g on both sides, lowercase g. So we get this equation. Then we're going to square root both sides. So r equals the square root of capital G mv over lowercase g. So there is our formula. So now that we have that, we can plug in our different values, and r is going to equal 6.67 times 10 to the exponent negative 11, and then the mass, which is 4.867 times 10 to the exponent 24, over gravity, which is 8.87 on Venus. So this is the radius. Now this is in meters, right? So 604,967.1. No, 1.323. Okay, now if we want to get it into kilometers, this is meters, right? We want it in kilometers to compare to the other planets. It would be this. So that is the radius of Venus. Now, if you compare it to the other planets, you can see that it is pretty close to Earth's radius and significantly larger than Mars's radius. Right? And this is interesting. Why are we going to Mars if Venus has such a close gravity to Earth? Shouldn't we go to Venus? It's a better planet, right? But there are problems with Venus. The biggest and most important is it is super hot and toxic. So if you go there, you'll basically die because you'll get squished with the air pressure, and it has toxic atmosphere and corrosive atmosphere. I think like acidic type of thing, like corrosive. It's not very good, and it's super hot on the surface of Venus. The greenhouse effect is off the charts. So Mars is actually better because of that, but not because of gravity. Venus is the closest to an Earth-like planet we have, if we're specifically only talking about gravity. All right, so I hope this video helps you better understand gravitational fields. Basically, just a real quick recap. Whatever your mass is, so if this green blob is your mass, right? The gravitational field is just a field that's pulling everything towards it. And you can calculate the field strength at any given moment by being able to say, hey, this is the radius. So once you know the radius away from the mass, away from actually the center of the mass, you're able to find the field strength at that point. That is what we're doing in this unit, or in this topic. I hope this video helps you better understand gravitational fields, and good luck.